K means found hidden groups in our data. PCA tackles the other great unsupervised problem, too many dimensions. Real datasets can have hundreds of features, and our eyes give up after three. PCA finds a small handful of new directions that capture most of what's going on, letting us compress data, cut noise, and finally see high dimensional data on a flat screen. Here's the trouble. Suppose each example has dozens of features. You simply cannot plot that, and worse, many of those features are redundant, quietly measuring almost the same thing. Height in centimeters and height in inches would be a silly extreme, but real data is full of softer versions of exactly that. PCA's core idea is to look at the cloud of data and ask, along which single direction does it spread out the most? That direction of maximum variance is the first principal component. It's the one new axis that, on its own, preserves as much of the data's spread as possible. Then it asks for the next direction, the one with the most remaining variance. But with one rule, it must be at right angles to the first. That's the second principal component. Keep going, and you get a fresh set of axes, each one capturing less and less, all perfectly perpendicular to each other. Now the magic. We project every point onto just the first couple of components. We describe each example by where it falls along those new axes and throw the rest away. We've gone from dozens of numbers down to two while keeping most of the meaningful variation. That's dimensionality reduction. How many components should you keep? Each one comes with an explained variance ratio, the fraction of the total spread it captures. You add them up and keep just enough components to cover most of the variance, often 80 or 90%. A handful usually does it. A couple of honest cautions. The new components are blends of your original features, so they are powerful but harder to interpret directly. And because it's all about variance and distance, you should almost always standardize your features first. Used well, PCA is brilliant for visualizing, for speeding up other models, and for quietly removing noise. In Scikit-Learn, it's clean. A standard scalar, then PCA with end components, and fit transform to get the reduced data. Afterward, explained variance ratio tells you how much you kept. Let's reduce the classic iris dataset from 4 dimensions down to 2 and write it. Here's the program. One page, every line visible. It's short, but it does something genuinely powerful. It squeezes 4 dimensions down into 2 that we can actually look at. Let's read it. The imports load iris to get a real 4-feature dataset, standard scalar for scaling, and PCA from sklearn dot decomposition. That's the star of the show today. We load the iris dataset. X holds 4 measurements for each flower, petal and sepal sizes, and Y holds the species. We'll only use Y at the very end to color the plot. PCA itself never looks at the labels. Then we standardize. Because PCA is all about variance and direction, we put every feature on the same scale first, so that no single measurement dominates simply for being on bigger numbers. And here's the heart of it. PCA with end components equals 2, then fit transform on the scale data. In one line, every 4-dimensional flower becomes just 2 numbers, its position along the first 2 principal components. We print the explained variance ratio, the share of the total spread that each of our 2 components captured. For iris, those 2 alone hold the great majority of the information, which is why this works so well. Finally, we plot those 2 new dimensions, coloring each point by its species. and the famous result appears. The three flower types fall into clearly separated groups, and remember, PCA never saw a single label to get there. And that's PCA. Find the directions of greatest variance, project onto a few of them, and keep most of the meaning in far fewer numbers. It's the go-to tool for visualization and compression. Next time, we stop studying single models and start assembling the full workflow, pre-processing and pipelines.